Hey friends, and welcome back to another video. In today's beginner's guide, I want to give you a brief overview about Computational Fluid Dynamics, short CFD. Quick note here, the visualization that you can see on this slide is a simulation of a flow around the nose landing gear of a Boeing 777, which was a cooperation between NASA and Boeing, and this simulation has been carried out on a supercomputer. So the agenda for today looks as follows. Of course, as always, I will give you a short overview about the historical background. Then we will answer the question, what is computational fluid dynamics, short CFD? Why do we use it and how does it help us in the product development process? I will briefly talk about what the mesh is and what type of meshes exist. I will go into the governing equations and how we could solve them theoretically. I will very quickly introduce you to the concept of boundary conditions. I will also talk about turbulence, how we can understand it, and give you a brief overview of what models exist. At the end, I want to give you some book recommendations. So let's jump right into it. Some information about the historical background of CFD. So in 1768, it basically starts with Leonhard Euler, however you want to call him, who introduced the finite difference technique, which is based on the so-called Taylor series expansion. We will do a big jump straight to 1922 to Lewis Fry Richardson. In 1922, he created the first numerical weather prediction system. He also worked on stress analysis on a masonry dam. What he did is that he built a team of small boys who were good at arithmetic, and he called them computers. The factory, if you want to call it like that, would have filled a vast stadium with 64,000 people. Each one of them was armed with a mechanical calculator and would perform specific operations. And there was a leader in the center who used a colored signal light and telegraph communication. And this leader would basically communicate and coordinate the forecast. Richardson carried out trial calculations while he served as an ambulance driver in World War I. He calculated winds over 100 miles per hour, but at that day, unfortunately, it was very calm, so Richardson did some errors in his calculations, but the physics was correct. However, the arithmetic he did was not quite accurate. And what he encountered as well were so-called instabilities, which were later on solved by the famous John von Neumann and Robert Richtmeier, by stabilizing shock waves with so-called artificial viscosity. A famous quote or poem from Richardson, which refers to turbulence motion, is the following one, where he said, "Big whirls have little whirls, which feed on their velocity, and little whirls have lesser whirls, and so on to viscosity." And we will talk about that in more detail in either a turbulence video, which is dedicated to turbulence, or if we talk about the so-called energy cascade. Here is a picture of the weather forecasting factory by Richardson. This has been drawn by Stephen Conlin in 1986 and was taken from the European Meteorological Society. And if you have a closer look at specific areas, you can really see the boys doing arithmetic and some other very interesting scenarios. In 1933, a man named Tom came by and he did the earliest numerical simulation with a cylinder, and he calculated the flow past the cylinder. You can have a look at the publication from Tom, and the title is given below. In the 1940s, John von Neumann did stability analysis of numerical schemes. He created the architecture also known as the von Neumann architecture. Talking briefly about the stability analysis von Neumann did, the analysis is based on the so-called Fourier decomposition of numerical errors and was developed at Los Alamos National Laboratory. Von Neumann also was the guy who continued, as I mentioned, Richardson's work of weather forecasting at the Princeton Institute, where he used the computer or machine called ENIAC. And he did the first successful computation for a one-day local forecast, and it took around 24 hours to run the computation. In 1950s, we have Sergei Godunov, and he proposed solutions of conservative laws in case of discontinuities, also known as shock waves. And he showed that in case that the order of accuracy of a method was p bigger than 1, where p denotes the order of accuracy, the calculations carried strong oscillations. And for that, he developed the Godunov type methods. And the basic idea is to look at the information transport as some kind of acoustic wave traveling from cell to cell. In 1960s, the Los Alamos labs, based in New Mexico, developed some very important models and techniques, some of them also used to this date. For instance, the K-epsilon model. Then we have the particle in cell method, short PIC. We have the vorticity stream function methods, as well as the arbitrary Lagrangian Eulerian methods. For those of you who do not know what the Los Alamos labs are known for, this is also the place where the first atomic bomb has been developed. In 1963, we have Joseph Smagorinsky, who carried out the first large eddy simulation, short LES, in meteorology. Then, in the 1970s, we have Dudley Bryan Spalding. There was a group working for him at the Imperial College in London, and they developed the parabolic flow codes named GenMix, and the very famous SIMPLE algorithm, still used to this day. And SIMPLE stands for Semi-Implicit Method for Pressure-Linked Equation. And we have the K-epsilon modeling, which is used today, so the one from the Los Alamos labs has been modified. We have a very well-known technique called upwind differencing, which was developed there, and we have the eddy breakup combustion model coming up. Some other historical background information. In 1956, Peter Lax defined the so-called equivalence theorem. Don't worry too much if you don't know what consistency and stability as well as convergence here means. We'll cover that in a separate video talking about numerics. In the 1970s, we have MacDonald and McCormack, who invented, so to speak, the finite volume method to solve the Euler equations. And then we have in 1972, Orhan and Patterson, who did the first direct numerical simulation, short DNS, of the time-dependent 3D Navier-Stokes equation. Quick side info as well, this DNS simulation by Orhan and Patterson was carried out on a 32 by 32 by 32 grid, and they used a so-called pseudo-spectral method. Jumping straight to 2013, we have the world's first cloud-based simulation platform, namely SimScale, which allows you to perform simulations right inside of your browser and then send your simulation straight to the servers, which will run the calculations for you. So how does CFD help us in the product development process? First of all, we have to define what CFD stands for, and CFD is a field in fluid dynamics that incorporates numerical analysis to simulate and solve problems involving fluid flows. In general, and what you have to take care of, is that we deal with partial differential equations which model nature, and these are continuous. In order for our computer to solve these partial differential equations, we have to transform them, so to speak, in so-called a system of linear equations, and then we solve this system with some direct or iterative methods. I will later on talk about some methods that you should know about. And with today's computational power available, very large of these systems of equations can be solved. Please also note that this is always an iterative process, as I've also shown you in the FEM video, so you cannot run one simulation and then be happy with it. So you always have to go back to the beginning, make some adaptations, and then continue the process until you are satisfied with your results. That's why we also have this funny but also at the same time sad quote. So CFD also is known as so-called colors for directors or colorful fake dynamics. And what that basically means is quite simple. We can always generate nice colorful pictures, but at the end it's our responsibility or the responsibility of you, the user, to make sure that these colorful pictures actually make sense. Why do we use CFD? So we can use CFD in order to overcome this prototyping process at the first place. Of course we need prototypes, but we can make sure that these appear at a later stage of the development process, and we also can be adventurous by, let's say, optimizing parameters on the fly and see what effect they have inside of our machine without having to embarrass ourselves in front of colleagues, for instance. And here you can see a fluid flow simulation carried out on SimScale, on the SimScale platform. For that we use the so-called Lattice-Boltzmann solver. So how does CFD help us now? As I mentioned, we have at the beginning the CAD model that we want to simulate, and in the usual product development process and how it has been done earlier is that you have the prototype, test it, redesign it, which is quite costly and time consuming, and we can reduce the cost as well as the time in order to build the product by using simulation. Please be very careful here when we say divide and conquer. We use this term when we introduce the finite element method in our other beginner's guide. However, divide and conquer means something different here. First of all, we have our domain, and this continuous domain is discretized into simple geometric shapes, which we call cells, and we call this whole domain, which is discretized, also the mesh. And the goal is to have a volume that is so small that certain quantities inside of that volume stay constant. Vertices or faces appear on the element boundaries and fasten the elements or volumes together. And divide and conquer, as I already mentioned, is generally not referring to the approach, how we want to solve our problem, but it's referring to the parallel computation, which means that we subdivide our domain, give each processor a specific domain, and let the processor calculate this domain or solve this domain, and at the end bring everything together and let the processors communicate between each other so that we have the final solution at the end. Some terminology to make sure that we are on the same level when we talk about these words. First of all, we have the vertex, which is a point, and the plural of vertex is vertices. We also have the face, and we also have the edge as well as the volume, as you can see on the lower side. We can also take this whole cube as the volume. However, this volume has been subdivided into 8 volumes, so we can take the smallest volume in this case as the volume. So steps in the CFD analysis look as follows. First of all, we have the physical problem, and we have to transform it into a mathematical model, also known as partial differential equations, as I've already mentioned. Then we perform the meshing operation, which is also known as the pre-processing phase. Then we define the analysis type we want to perform, if it's either compressible analysis type, incompressible, multi-phase, or anything else. Then we specify the fluid properties as well as the boundary conditions to have a well-posed problem. Then we select our numerical schemes. Usually the standard schemes work quite well, however sometimes we have to make adaptations. And what do I mean by numerical schemes? We basically select our solvers and interpolation schemes for the solution of the equation system. And at the end we can post-process our results, have a look at, for instance, the pressure loss, gain, vorticity, or forces acting on our component. On this slide I want to give you a short review about the steps involved in the CFD analysis. So we have the real-world problem, which will be transformed into a PDE, and then we have a system of algebraic equations. We implement that into our machine, we generate the data, and then at the end we can post-process our results. So the mesh is the discretized version of our computational domain. We also call that grid. And there are 2 approaches possible. The first one being the top-down approach, where we have logical operations on our geometry primitives like a cylinder, box, or a sphere. So if we define these geometry primitives, the mesh will be built according to these geometries. The other approach is the bottom-up approach, where we first create the vertices, then from these vertices form a line, also known as edge. From this edge we create a face, and from this face we can create volumes, or faces. In this case we can create the volumes. Cell types available in the CFD analysis look as follows. We of course have 2-dimensional elements like the triangular elements and quadrangle elements, also known as tris and quads. And in case of a 3-dimensional simulation, we have the tetrahedrons, also known as tet elements. We have the hexahedrons, also known as the hex elements. We have pyramids and also wedge elements. We can also make a distinction when it comes to grid types. So in this example here, having a look at the upper mesh, this is a structured non-orthogonal grid. The second one is a 2D block structured grid, where we can use that approach to perform a simulation where we have a cylinder in the middle, and then perform a simulation where we have flow around the cylinder. And as you can see, we have 3 blocks, this one being the first block, then the second block, and the third block right here. And what you can see is that these blocks match at the interfaces. And the third mesh type that I want to show you, of course there are a bit more, but the third type, which is an exotic mesh type, is the so-called composite or so-called chimera grid. And I will list some types now. So we have orthogonal meshes, non-orthogonal meshes, we have structured meshes, block structured mesh. We also have the subdivision of H, O, and C meshes. Also a combination of them is possible. We have, of course, unstructured meshes as well as hybrid meshes. And we have so-called immersed boundary meshes where we immerse our geometry into the mesh. And we have, as I mentioned, the chimera mesh, or also known as composite mesh. So talking about the Navier-Stokes equations. So first of all, we have the so-called conservation of mass, which says nothing else that mass is not created or destroyed. The very first term on the left-hand side is the change of mass in time. Then the second term is the flow of mass through our boundaries, if we have a look at the very infinitesimal volume. And on the right-hand side, of course, equals 0, because we want to say that mass is not created or destroyed. That's the conservation of mass. Then, of course, we have the conservation of momentum, with the change of time at the very left side. Then we have the so-called convection term, which gives us a few problems later on, which also is a nonlinear term. Then on the right-hand side, we have pressure and viscous forces, as well as extra forces acting on our fluid, like gravity, for instance, or you can add other forces as an additional term, for instance, Lorentz forces in case of magnetohydrodynamics. We can also rewrite this equation as follows. So we have the left-hand side as it is, as I've shown you, and the right-hand side is nothing else than the sum of the forces. This equation should be quite familiar to you. That's nothing else than Newton's second law of motion. And in another beginner's guide, which will come in the future, I will show you how you can use Newton's second law of motion and really derive the Navier-Stokes equations by having a look at a volume. Please note that this is not only one equation that we have to solve, but 3 equations, because we have 3 spatial directions, usually namely x, y, and z. And also we have the conservation of energy, but that will be covered in the beginner's guide, where I talk about the Navier-Stokes equation in particular. A bit of history about the Navier-Stokes equation. So fluid motion itself has been known for a long time, of course, but however, the mathematical models emerged at the end of the 19th century, after the Industrial Revolution. And the initial appropriate description of the viscous fluid motion has been indicated in the paper Principia by Sir Isaac Newton, who can be seen on the very left side. And Newton basically investigated the dynamic behavior of fluids under constant viscosity. Later on we had Daniel Bernoulli as well as Leonhard Euler, who derived the equation which later on became known as the so-called Euler's inviscid equation, even though Claude-Louis Navier, Cauchy, Poisson as well as Saint-Venant had carried out studies to explore the mathematical model of fluid flow. They had overlooked an important thing, which is viscosity, or also known as frictional force. And then in 1845, Sir George Stokes had derived the equations of motion of a viscous flow by adding Newtonian viscous terms. And thereby, the Navier-Stokes equations had been brought to their final form, which is known today. Now I want to talk about approaches how to solve these equations. So we have 3 different methods that we can use: FEM, FDM, as well as FVM. FEM stands for finite element method, as you might know, and there we start with a weighted integral form of the transport equations. FEM can also be used in CFD, but it's not very common. Then we have the finite difference method, FDM, where we start with a differential form of the transport equations. Last but not least, we have the FVM, also known as the finite volume method, where we start with the integral form of the transport equations. This method is also known to be conservative. That's because we use the integral form and not, for instance, the differential form. So we said that FEM is not that relevant, and if we use one of both methods, like FDM or FVM, we get the following system of equation, which looks like this. So almost looks like A times X equals B, and I'll just have rewritten it in a more general form, A times phi equals Q. Here we have the equation again, and we can solve this by using either direct methods or iterative methods. As for the direct methods, we can use something like the Gauss elimination or LU decomposition, or something like the tree-diagonal algorithm, also known as TDMA, which stands for tree-diagonal matrix algorithm. And as I mentioned, the second type would be iterative methods, where we have something like SOR, which stands for successive oral relaxation, ILU, incomplete LU decomposition, or ADI, also known as alternating direction implicit. When it comes to specific fluid flow types, we have the following ranking, where the boundary layer flow is the easiest to solve, and then at the end we have the compressible Navier-Stokes equation, which are the most sophisticated ones, if you want to call it like that. And this is how the complexity or the effort in terms of simulation effort increases. Jumping right into turbulence, where we have Leonardo da Vinci, who drew this picture, and as you can see, he also had a look at turbulent motion. And da Vinci said the following thing: observe the motion of the surface of the water, which resembles that of hair, which has two motions, of which one is caused by the weight of the hair, the other one by the direction of the curls. Thus, the water has eddying motions, one part of which is due to the principal current, the other to the random and reverse motion. So what are the characteristics of turbulent flow? Turbulent flow is very irregular, and chaos is involved in turbulent fluid flow. It's a three-dimensional phenomenon, also due to the fact that we have an effect involved called vortex stretching, and we will talk about this effect in a separate turbulence video. We have enhanced mixing effects. We have the so-called energy cascade, where we introduce energy in our system with large eddies, and then energy is going down to the small eddies, so the large eddies break up into smaller eddies, and then at the molecular scale, the energy is being dissipated as heat into our system. Please note that you should not say that energy is destroyed at the small scales. That's not correct, but we rather say that the energy that we introduce in our system is converted into heat. And that's what also is meant by the last point, that the turbulent motion is also very dissipative and is a dissipative process. So how can we distinguish turbulent flow from laminar flow, or also known as non-turbulent flow? What we can use, and what's often used, is the so-called Reynolds number, which is a dimensionless number, and they give us a relation between inertial forces and viscous forces, where we have the inertial forces in the numerator and the viscosity in the denominator. So we have U times L divided by nu. And we say flow is laminar if the Reynolds number is low. And then the question also is, what is low? So you really have to have some experience in this subject, also to know in order to determine if the flow is really turbulent or is it still laminar. Let me give you an example. We have the very famous Reynolds crit of 2300 for pipe flow, where we say that laminar flows goes over to turbulent flow at this Reynolds number. Please note that there's no quick jump between laminar and turbulent, where you say, okay, I have laminar, and at that point I immediately have turbulent flow. Rather, we have a so-called transition between laminar and turbulent flow. However, we have one problem. Let's imagine we measure flow, or the velocity in our flow, then we come up with the following signal. And the problem is that turbulence consists of random fluctuations, and for that we have to use statistical approaches to tackle this problem. And on the right hand side you can see the so-called Reynolds averaging, where we say that the velocity is nothing else but the mean of the velocity plus a fluctuation part which depends on time. And this Reynolds decomposition was introduced, of course, by Reynolds. And as I mentioned earlier, you know that the Navier-Stokes equations have a nonlinear term in them. And this leads to the appearance of so-called momentum fluxes. And these momentum fluxes act as apparent stresses throughout the flow. And however, we don't know these momentum fluxes a priori. And if we derive equations for these momentum fluxes, which are unknown a priori, we include additional unknowns into our equations. And this is what's the so-called closure problem. And in order to overcome this closure problem, we have to use models. And we have models like, for instance, the Reynolds Average Navier-Stokes equation, which come from averaging the equations, where we have to model some of the behavior of the turbulent flow. And then we have, in terms of complexity, the next step would be the detached eddy simulation. Then we have the large eddy simulation, where we resolve the large scales but model the small scales. And then the most complex one is the direct numerical simulation. Please note, and I say this very clearly here, that although I have written model effort in the title, DNS is not a model. That's a very common mistake that people think and make. DNS is no modeling, so no models are involved in DNS. It's a technique used to resolve all the scales of our fluid flow. With the transient versus the steady state approach, and for the transient approach we can say that density is a function of time and space. So we have to deal with this equation and cannot make further simplification. However, if we have a look at the steady state equation, we can say that our time dependency vanishes, and then we have delta rho ui divided by delta xi equals 0. There, density is only a function of space but constant in time, and we can make even further simplifications where we can say that our density is constant. Then we can divide by the density. Then we would have the equation delta ui divided by delta xi equals 0. As for boundary conditions, I have used the same slide as for the finite element method introduction. And what's relevant for us in this case is the CFD row, where we have a Dirichlet boundary condition in case we prescribe velocity and or pressure. Neumann boundary would be something like a symmetry plane, where we said that du by dn equals 0. And we have a Robin or Robin boundary condition in case of a semi-reflective wall. Some books to you that I would recommend in case you want to have a closer look at the titles. Feel free to pause the video right now. And with that being said, we will jump to potential video topics for the future. So we can talk about turbulence, and I can create a beginner's guide for you, how we solve the problem of turbulence, solve quote unquote, because it's quite difficult. We can have a look at wall functions and what the so-called y plus value is. I also told you that we can have a look at the derivation of the Navier-Stokes equation with Newton's second law. We can have a look at how to program a simple finite difference case, where we have a look at stability and have a look at the so-called Peclet number. We can also do some CFD course on how to use OpenFOAM, like a commercial code that you can use for your projects. I can tell you how to properly manage a CFD project using a very simple tool like Excel. And we can also deal with post-processing, where I can show you how you use ParaView. You can find already one video on my channel, how to use ParaView for contour plots. And a very interesting topic as well are the so-called stability criteria, where we can have a look how to derive stability criteria and what the so-called CFL number is and what it stands for, and how to physically interpret it. If you have any other ideas, please put them down under the video and I would be happy to discuss them with you. And as always, you can find the slides on my Patreon page, and you can also have access to other material. There we have the sources of pictures. And that's it for this beginner's guide on computational fluid dynamics. If you have any questions, comments, thoughts, please put them down in the comment section. If you haven't subscribed already, please do so. Invite your friends. Please share the video. Also give it a thumbs up. And as always, make sure to keep engineering your mind, and see you in the next one.
Bye.